Hello, we are Caffeine is all we need, and for our final project, we address the AG news classification task using LSTM and transformer encoders. Um, First thing first, AG news is a benchmark dataset for news topic classification. The name comes from the original AG's news corpus, which contains news articles collected from more than 2,000 sources. The benchmark version selects the four largest categories from this corpus. So there are word, on the right side, you can see the word, sports, business, sci-tech, like that. If you look at the right side, the four word clouds, that shows most discriminative tokens for each class. Keyword searches such as NASA, stocks, and coach are highly class specific, um, and this leads to questions. So the first question, research question is, does this task truly require word order? And second, do LSTM and transformer model differ in how much they rely on word order? So to answer this question, we did experiments along two axes. First, model variation, and second, input variation. To make a fair comparison, we kept all the other settings at the same model, like tokenizer, data source, maximum sequence length optimizer, batch size, and training budget, so like 8 epochs. So we built the same vocabulary for the training dataset, and we selected the best model based on validation macro F1 score and used the test set only for the final evaluation. The two baseline models are also similar in size with 3.48 million parameters for the LSTM and 2.83 million for the transformer. Our first experiments start with LSTM, which is the baseline. It uses an embedding, two-layer unidirectional LSTM. So last hidden, state pooling, then linear classification, as you can see the sequence on the top. So the baseline is embedded 128 and hidden was 256. Two layers drop out 0.3, so the 30% of the parameters are dropped out, and about 3.848 million parameters is the baseline of our model. And the key property was LSTM explicitly order sensitive by construction. It consists of some of other transformer models. So these are transformer models. So there's same sequence on the top, token IDs to linear and for classification with logit scores. And the baseline was same embedding dimensions and same number of layers, but for the transformer we manipulate with four heads and same dropouts, and then the final baseline version was 2.83 million parameters. So contrast with the LSTM, it has a specific property that the encoder computes how all words related to each other directly and classifies from the pooled representation. At a similar parameter scale, the transformer achieved the task macro F1 score of over 0.9, which is 0.911199, compared with 0.9137 for LSTM. This is a difference of about 0.6 percentage point, and the improvement is not a large scale, but it is consists across runs. So the loss curve also help explain this result. As you can see on the right side. And in contrast, so LSTM overfits more strongly, and in contrast, the transformer maintains a small gap between training and validation loss. Within the same 8 epochs training budget, it shows more stable generalization. On the model side, we conducted a sequential ablation study for the LSTM and transformer. At each step, we selected the best configuration based on validation performance before moving to the next hyperparameter. So first, increasing the embedding size led the gradual improvements, and 256 dimension was selected as a best value. Dropout had only small effects, so with zero point 0.1, so 10% of dropping out was the best performance in LSTM, and increasing the hidden size also improved performance, but the gains become smaller beyond about 512 dimension. The best results was obtained at the hidden size of 768. However, the validation selected 922 as the best setting. So with this large configuration, the LSTM reached a macro F1 score 0.9189, but the model size increases to 16.228 million parameters. So overall, LSTM improves gradually as we increase its capacity, but it requires substantially more parameters to reach its best performance. So this leads to efficiency comparison on the next slide. For the transformer, we varied same factors as LSTM, and overall, the validation selected transformer achieved a test macro F1 score of 0.9215 with only 1.38 million parameters. So this makes it roughly 12 times more parameters efficiency than LSTM. For our invalidation study, we used three conditions that differ only in word order. So the first condition is original input, and second one is local shuffle, where we shuffle words only within small windows of 5 tokens. The third is full shuffle, where we randomly reorder all tokens in the sentence. To make the comparison controlled, we keep the vocabulary, tokenizer, and all the other parameters at the same. So we evaluate each condition using same as before, F1 macro score and F1 drops compared with the original input and on order sensitivity ratio. So overall, the study includes 3 input conditions, 5 random seeds, and 2 models for a total 30 runs. The main results is the removing word order has a surprisingly small effect on performance. Under full shuffle, the LSTM drops by about 1 percentage point, while the transformer drops less than half points. This suggests AG news classification is driven largely by topic-related keywords rather than by an order of the word. However, the LSTM is clearly more affected by shuffling. For both models, performance decreased consistently from original to local shuffle to full shuffle, but the LSTM drops about 3 times more than a transformer. This is interesting results because transformer trained and tested on fully shuffled tasks still perform better than original LSTM. So for the result, we compared both models on the same 7,600 test example. The two models agree on many cases, and they are both correct on 89% of the test set and both wrong with 5%. So these shared errors are likely caused by ambiguous example, overlapping class boundaries, or possible label noises. So to conclude, both models remain surprisingly robust even when word order is removed. So their performance drops by less than 1 percentage point, which suggests that agent use is mainly a topic classification task driven by lexical cues and keyword. However, the two architectures respond differently. LSTM is clearly more sensitive, and Transformer was much more robust. And the Transformer is also much more parameter efficient. So this achieves strong performance with roughly 12 times fewer parameters than the selected LSTM, and it shows more stable generalization during training. So there are some, and also there were some limitations. Our hyperparameter search was sequential rather than fully factorial, and we only tested data scaling for transformer. So in the future work, we plan to run match scaling study for the LSTM and train both model for longer and include bidirectional LSTMs. So yeah, thank you for listening.